be introducing the concept of entropy. What is entropy, you ask? Well, entropy is used to express the randomness or disorder of a chemical process. The more random and disordered, the more entropy the process has. Now I would like for you all to imagine two scenarios. Each scenario contains two 1-liter flasks that are connected with a stopcock. Inside are 3 gas molecules. Well, in scenario A here, the stopcock is closed. The molecules here can only move on this side of the flask, making it harder for them to arrange themselves differently. In scenario B here, the stopcock is open. As you can see, there are 8 different ways that these molecules can arrange themselves. More disorder, more randomness, more entropy. Now I'd like to bring you back to the concept of kinetic energy and demonstrate how kinetic energy and entropy relate to one another. In chemical kinetics, when a substance starts at a solid, moves to a liquid, and ultimately then to a gas, kinetic energy is increasing. This is the same case for entropy. Now I would like to help you visualize this concept. I'm going to be doing that by showing you how entropy increases when H2O molecules start in the solid form, move to a liquid form, and ultimately to the gas form. Imagine this cup of ice is a room with 100 people. As you can see, there's not a lot of room for these H2O molecules to move freely. They're all compact, they're frozen, they're stuck together, not a lot of range of motion for these H2O molecules. Imagine this room with 20 people. Obviously, the less people, the more room for them to move around, like this glass of water. It's dissolved H2O, which means there's a lot more room for these molecules to flow. Now, would you think entropy would increase or decrease as the H2O goes from a liquid to a gas? We'll take a look. As you can see, the water is boiling. This definitely makes it easier for the molecules to jump around, making it more random, making it more disordered, which is why in the gas phase, entropy is always highest. Entropy is symbolized as delta S. To calculate for standard entropy, we subtract the total amount of entropy in the reactants from the total amount of entropy in the products. So let's visualize this here. In the reactant side, we have 3 moles of substance A, 2 moles of substance B. In the product side, we have 4 moles of substance C and 5 of substance D. This is how you would solve for this equation. You take the products first. We have 4 moles of substance C, and we add that to the 5 moles of substance D. Then we'll subtract the 3 moles of substance A plus the 2 moles of substance B, and that will ultimately give us the answer for our delta S. Now let's talk a little bit about spontaneity. Well, if the value of delta S is negative, it's non-spontaneous. If the value of delta S is positive, that means it's a spontaneous reaction. Well, what does that mean? A spontaneous reaction reaches completion without any outside intervention. It's the opposite for a non-spontaneous reaction, however. A non-spontaneous needs constant work put into the system in order for the reaction to reach completion. So the second law of thermodynamics provides us with a straightforward approach to determining spontaneity. Okay, so the direction of a spontaneous change is always determined by the sign of total entropy, which is labeled as delta S universe. So how to solve for delta S universe, we use this equation. We take the entropy of the system plus the entropy of the surroundings in order to solve for the total entropy. The second law of thermodynamics also states that the delta S of the universe is a closed system and that it's always increasing. Not to travel too far off track, but I want you to visualize what a closed system is and an open system. For an open system, I want you to picture a campfire. So we have the logs, the flame. Well, the campfire is in an open space. Its surroundings are interacting thermodynamically with the system. The fire is releasing heat, it's releasing light, The surroundings in the system are interacting. You never know. Here in a closed system, picture a cooler filled with ice. The cooler is shut closed, so the system is isolated from the surroundings. The surroundings have no effect on that.
Now, we just saw there was a spontaneous combustion reaction. Now, a simple ignition was needed to begin the reaction, but there's no need for outside input in order to complete the reaction. The system of this reaction is potassium perchlorate and sodium benzoate. Now, during the reaction, the system is releasing energy to the surrounding, so the surrounding is gaining the energy much faster than the rate of the system decreasing. Therefore, delta S entropy of the universe is positive.
So this question asks for the standard entropy of a reaction at 25 degrees for the Haber synthesis of ammonia. So this reaction has nitrogen gas plus 3 moles of hydrogen gas producing 2 moles of ammonia gas. Okay, so we will first approach this equation by finding the standard molar entropies of our reactants and products, which can be found at the back of your chemistry book. So, for our reactants, we have hydrogen and nitrogen gas. The standard molar entropy of nitrogen is 191.5 joules per mole Kelvin. The standard molar entropy of hydrogen gas is 130.6 joules per mole Kelvin. Then we move to the products. Our products is ammonia gas. The standard entropy of ammonia gas is 192.3 joules per mole Kelvin. Now that we found the standard molar entropies of our reactants and products, we can start talking about how we're going to set up this equation. So, delta S is products minus reactants. For our products, we have 2 moles of ammonia. In our reactants, we have 1 mole of nitrogen and 3 moles of hydrogen gas. So we would set it up like this. Ammonia is the product, so we would put it on the left side. There's 2 moles of ammonia, so we would do 2 times the standard molar entropy of ammonia here. Then we would subtract the value of 1 mole of nitrogen gas plus 3 moles of hydrogen gas. Before we solve for delta S, let's try and predict whether or not it's going to be spontaneous. Well, each of these gases are in their standard state, because it said previously it was 25 degrees Celsius, which means it's 298 degrees Kelvin, which means these gases are in their standard state. So we can predict this because we see here, we have 2 moles of product versus 3 plus 1. 4 moles go to 2 moles. So if we take 2 minus 4, are we going to get a negative or a positive answer?
A negative.
That's right. And what does it mean if we get a negative value for our delta S?
Non-spontaneous.
Molar entropies for our reactants and products, and we've set up how to properly solve this equation. Let's plug and chug. So we have 2 moles of our product ammonia, which has a value of 192.3 for its standard entropy. 2 times 192.3 comes out to 384.6. Now let's see what we get on this side. We do 191.5 times 1, since there's only 1 mole of nitrogen gas, plus 3 moles of hydrogen gas with a standard molar entropy of 130.6. Now when we solve for this part, we get 583.3. Now, let's see what we get. 384.6 minus 583.3 equals negative 198.7 joules per mole.